Hello and welcome back. We'll continue looking at discrete probability distributions. And here we'll start out with the expected value. And this is just another name for the mean. So the expected value of a random variable is just the mean. And I'll go through something to explain this more at the end of the lecture. But essentially, anytime that you want to calculate the expected value of something, the expected value is just the mean, which we have the formula for. You just take each value that the random variable can take times the probability that it occurs, and we sum it all up. Now, just as a caveat, sometimes the expected value might not be a whole number, even though you would expect a whole number of things to happen. So, for instance, when you flip 5 coins, the expected number of heads would be, you'd expect about half of them to be heads, but half of 5 is 2.5. Well, you can't get 2.5 heads out of 5 coin flips. You can never get half of the heads. So this doesn't necessarily make sense in terms of thinking about it literally, but this is only the expected number. So if you'd expect 2.5 heads, maybe this means, getting 2 or 3 seems pretty reasonable. So even though this is a decimal, we can still interpret that. So I just wanted to go through another example of calculating mean and standard deviation. So again, the mean for a probability distribution, a discrete probability distribution, is going to be the value times the probability that it occurs, and then we sum all of them up. So here I have the number of 6s rolled on a 6-sided die that we've rolled three times. So if you roll 3 dice, you could either get 0 6s, 1 6, 2 6, or 3 6s. All 3 of them could be 6s. Here are the probabilities for each one. In the next section, we'll see how to come up with these probabilities, but for the moment, these are what they are. And what we need to do is calculate each value times the probability. And these aren't too bad. 0 times anything is always 0. 1 times anything is just itself. 2 times 15 216ths will be 30 216ths. And 3, well, that's just 3. Oops. So then when we add all of these up, so this is 75 plus 30 plus 3 over 216, leaving out the 0 because anything plus 0 it doesn't change anything. This is going to be 108 over 216, and that's exactly 1/2. So how many 6s would you expect to roll if you roll 3 dice? About a half of a 6. Well, a half of a 6 doesn't really make sense, so maybe a better way to interpret this would be either 0 or 1 6s. The expected value is exactly 1/2, but what this means is we'll get close to either 1 or 0. The standard deviation for a distribution, we normally calculate the variance first, and the formula that we will use is going to be very, very similar to the mean, except we want the value squared times the probability that it occurs. And then after we've summed all that up, we will subtract the mean squared. So what we need to do is calculate x squared times p of x for all of these. So 0 squared is 0, times anything is always 0. 1 squared times this number is just itself. 2 squared is 4, and 4 times this number will have 60 over 216. 4 times 15 is 60. And 3 squared is 9. 9 times 1 over 216, well, that's just 9, 216. So again, we will need to add all these up, which if I add 0 to anything, it doesn't change it. So this is going to be 75 plus 60 plus 9 over 216, and we're going to subtract the mean, which is 1/2 squared. So, continuing on, 75 plus 60 is 135, plus another 90, that's 144. 1/2 times 1/2, that's 1/4. And if we do a lot of simplification, I'll do this off screen, we get 5/12. Everything cancels out. This is in fact 2/3. So these numbers simplify down a lot. Now, the standard deviation is going to be the square root of the variance. We just cancel out the square root and the squared. So the square root of 5/12 is about 0.6. So here's our standard deviation, and here is our mean, which is going to be the same thing as 0.5. So we've just gone through a couple of these calculations again, and we'll look at a couple of different ways to tell whether or not values are going to be significant. We've seen this a little bit before, but we'll just go over this again. So as a rule of thumb, values that are more than 2 standard deviations away from the mean are considered significant, and significant in this case meaning unusual, or they should be taken into account. So wherever the mean is, if we add 2 times the standard deviation to it, and we're looking at numbers beyond this, so numbers bigger than the mean plus 2 standard deviations, or numbers smaller than the mean minus 2 standard deviations. These are significant, and these values are significant. So if we use the values that we had up here, our mean is 0.5 and our standard deviation is 0.6. So the mean value of 6's is 0.5. If we add a standard deviation to that, so 5 plus 0.6 is 1.1. 5 plus, so this again plus another standard deviation, which is 0.6, brings us up to 1.7. If we subtract 0.6, we'll get negative 0.1. And if we subtract another 0.6, we'll get negative 0.7. Now, we can't get a negative number of 6's. That just doesn't really make sense. But up here, for instance, 1.7, anything beyond 1.76's would be considered unusual given this rule of thumb. So for instance, if you rolled 2 6's out of 3, or if you rolled 3 6's out of 3 dice rolls, that would be considered unusual. It's beyond 1.7, so it's beyond 2 standard deviations away from the mean. This is one way, and this is a rule of thumb because this is oftentimes not going to be accurate enough. For things to be significant, just saying it's 2 standard deviations away isn't always going to be significant enough, especially, say, in science, in the medical field, when we need to make sure that things are very rigorous and very exact. So one other way to do this is to use probabilities. And the idea is that so x is going to count how many times something happens, and if something occurs x or more times, but the probability that we get x or more things occurring is less than 5%, is less than 0.05, that means that that was a significantly high number of occurrences. So this is x or more. And significantly low means that if we get x or fewer events to happen, and the probability that happened was less than 5%, that is a significant event. So I do want to emphasize that this isn't the probability that x that we get x successes here, that something will happen x times. This is x or more times, and this is x or less times. So let me give an example. I'll go through 2 examples. We're going to flip a coin 100 times. The probability of getting exactly 63 heads is pretty small. It's about 0.3%, 0.003. The probability of getting 63 or more heads is 0.006, which is also 0.6%. Now, so our answer, since 0.006 is less than 0.05, getting 63 heads is significant. If I can spell. So the number that we're looking at is the probability of getting 63 or more heads. To sort of explain exactly why we want to consider that, the probability of getting exactly 57 heads out of 100 flips is 0.03. So there's only a 3% chance that you could get exactly 57 heads out of 100 flips. But the probability that you get 57 or more heads is 0.097, which is almost 10%. So 10% of the time, about 10% of the time, you could expect to get 57 or more heads. That doesn't seem very unlikely. Getting 57 or 58 or 59 or 60 heads, the probability of getting 57 or more heads is almost 10% of the time. 1 in every 10 times that you would run this experiment, 1 in every 10 times that you would flip 100 coins, you would expect 57 or more heads. So getting 57 or more heads actually I want to be specific. Getting 57 heads is not significantly high. Since 0.097 is not less than 0.05. This probability is not small enough to make this an unusual event. So, and it's specifically the probability of getting 57 or more heads. Probability of getting exactly 57 heads is pretty small, but the probability that we want is 57 or more. And I'll go through one final example involving expected values. So here we're walking up to a roulette table, and we want to look at whether or not we should bet $5 on the roulette wheel spinning exactly as 7. When you bet $5, it pays out 180, and the odds of winning are 1 to 37. So the question is, what's the expected value of our winnings? Do we expect to win anything, or do we expect to lose something? So let's make a table. So the result of the roulette table, we can either lose or we can win. When we our net winnings. When we lose, well, we paid $5 for that, so it'll be minus $5. The net winnings when we win will be $175 because we had to pay the $5 and then we got back 180, so net we had 175. Now, so the net winnings is going to be our value for x. So the probability that x happens, the probability that we lose $5, well, if the odds of winning are 1 to 37, the probability that we lose, we're going to lose 37 times out of the 38 times. And the probability that we win is only going to be 1 in 38. So when we take x times p of x, we'll get negative 4.87. 175 times 138 is 4.61. And when we add these together, the expected value is going to be negative 0.26, meaning we expect to lose 26 cents each